Assalamualaikum warahmatullahi wabarakatuh. In this video, we will presenting our workshop project, which is peristaltic pump. First of all, we have 4 members in our group. First, Nur Adli Zikri bin Nawaza, Muhammad Uzair bin Yasmizi, Nur Aimi Farisha binti Zaman Huri, and Muhammad Zafran Amir bin. This is our content of slide presentations. Next, we move to work distribution. For part 1, housing casing, person in charge is Aimi and Uzair. They are dedicated to managing the fabrication of the pump's main housing block, initiating from raw stock prep to precise finish. Part 2, rotor bracket. The person in charge is Adli and Zafran. They are tasked with fabricating the driving rotation mechanism, which is rotor arm or assembly, and rolling accessories. And after part 2 is successfully fabricated, Adli and Zafran will join Uzair and Aimi to complete the part 1. What is peristaltic pump? Peristaltic pump is a highly efficient positive displacement pump designed to transfer various fluids safely through a flexible, specialized silicone tube. The operating mechanism relies on rotating rollers that continuously compress the tubing inside a circular casing. As the rotor turns, the pinch portion of the tube force the trapped fluid to move forward, while the subsequent relaxation of the tube creates a vacuum that draws more fluid into the inlet. The primary engineering advantage of this design is that the pump fluid remains entirely contained with the sterile tubing, completely eliminating any risk of contamination between the fluid and the pump components. Additionally, because there are no complex valves, glands or seals that are prone to wear down or leak, it represents a highly reliable, low maintenance system that is widely utilized in precision chemical dosing, medical device and hygienic food grade applications.
Moving on to our project mission and learning objectives. This slide outlines exactly how we bridge theoretical engineering with hands-on workshop execution, focusing on 4 core competencies. First, we have manufacturing planning. Our first objective is to take standard 2D engineering drawings and systematically convert them into a structure, step-by-step mechanical machining sequence. This ensures we have a clear operational roadmap before touching any machinery. Next is the physical fabrication. The ultimate mission here is to manufacture a highly precise, working physical pump assembly built entirely from mild steel raw stock. To achieve this, we will focus on skill integration. This project requires the practical, hands-on application of several workshop operations. First, we will start with raw cutting using a bandsaw. Move to concentric turning and boring on the lathe to handle cylindrical geometries. Utilize the milling machine for flat pocket profiling. And finally, perform fastener threading through precise drilling and tapping. Lastly, a quality assurance. A working pump requires absolute precision. Therefore, our final learning objective is to meet exact dimensionally criteria within a strict tolerance limit of plus or minus 0.05 millimeters.
Alright, next, Zafran here, and I'll be explaining about the safety equipments and techniques. So for safety equipments, we have 4 safety equipments: safety glasses, safety footwear, safety jacket, and safety gloves. For the safety glasses, it must be worn at all times to help guard against flying metal chips and splashes of coolant. For the safety footwear, steel-toed boots used to avoid injury from falling or heavy objects such as Alright, next for safety machining techniques. For lathe safety, always take off the chuck key after chucking the workpiece. The key can never be left in the chuck. Next, chip clearing. Clear sharp metal swath chips from the machine beds using a special hook or brush. Never use your bare hands. Next, secure clamping. Double check the workpieces and cutting tools made of mild steel were securely clamped prior to using the cutting.
Let's walk through the actual manufacturing process we execute on the lathe machine. The initial fabrication phase consists of 3 foundational steps to prepare our raw stock. Step 1 is facing. We begin by performing a facing operation. The primary goal here was to clean up the uneven end of the raw stock and create a perfectly flat, smooth reference surface for all subsequent measurements. Step 2 is the first boring operation. Once the face was through, we use an initial boring step primarily to mark the dead center of the workpiece. This acts as a critical guide to prevent any tool deflection later on. Step 3 is the second boring operation. With the center securely marked, we progress to our second boring pass, machining into the workpiece to an exact depth of 13 millimeters. Step 4 is the third boring operation. Here, we fine-tune our internal depth by taking a third boring pass, extending the internal cavity just slightly.
After completing the initial machining process, we proceeded with the next manufacturing steps. First, the workpiece was carefully marked according to the dimensions in the design drawing to ensure accurate hole locations before drilling. Next, side drilling was carried out using a drill press to produce the required holes while maintaining proper alignment. Finally, the unwanted portion of the material was removed using a hacksaw. This prepared the workpiece for the finishing operations in the following manufacturing stages. After the excess material was removed, the cut surfaces were ground to eliminate burrs and sharp edges, resulting in a smoother finish. The workpiece then milled to obtain a flat and accurate end surface that met the required dimensions. Lastly, the boring process was performed to enlarge and accurately finish the internal hole to the specified diameter. During the manufacturing process, our team encountered several challenges. The first problem was manual cutting fatigue. Because cutting thick mild steel with a hacksaw required a lot of physical effort and time. To overcome this, we rotated team members during the cutting process. The second challenge was machining the second inner diameter due to limited tool clearance inside the workpiece. We solved this by taking light cuts and frequently checking the diameter using a vernier caliper. The third issue was excessive friction during the lathe operation, which caused heat generation and affected the surface finish. We used cutting oil throughout the machining process to reduce friction, cool the cutting tool, and improve the surface finish. The fourth problem we encountered was workpiece instability during side drilling. Since the specimen was not securely fixed, it tended to roll or slip when drilling horizontally into the side, which affected both safety and drilling accuracy. To overcome this, one team member operated the drill press while another held the workpiece firmly in place. Both members wore safety gloves throughout the
Alright, finally for discussions, we will be discussing about the improvements that can be made. So these are our references that we used. Thank you so much for listening.